Nuclear binding energy is the energy required to remove all the particles, the protons and the neutrons, from the nucleus of an atom. So the way that we think about nuclear binding energy is it's really the work required. Remember, work is equal and opposite to potential energy. So it's the work required to remove every proton and neutron from the nucleus. Now, to calculate the nuclear binding energy, we need some sort of model to talk about the interaction that happens between the protons and the neutrons. And the best models that we have today are still evolving. So this is still very much a work in progress. So let's take a look at essentially what we're dealing with here. What are the forces which are holding the nucleus together, and what are the forces that perhaps can tear it apart? So here we see a very, very basic model of the nucleus. And the strong force is essentially the cohesive force that is holding the protons and neutrons together. It's an attractive force, but it's a force with a very, very limited distance, extremely strong. Okay, they weren't very inventive when they came up with the name, the strong force, but it does not have the range of other forces. Once you get on beyond about 1 Fermi, the strong force pretty much no longer has any influence. Also remember that we're dealing with protons here, and protons have a positive charge, 1.6 times 10 to the minus 19 coulombs. And at the distance that the protons are separated, this is a very large electromagnetic force. Again, our electromagnetic force, Coulomb's law, goes by 1 over the distance squared. And we're talking about distances of 10 to the minus 15 meters. We're talking about extremely large forces. So again, our cohesive force is a strong force trying to hold it together. The repulsive force is due to the electrostatic force. And the third force that actually plays a role is the weak force, but it plays sort of an indirect role in terms of it allows the nucleus to actually balance the number of protons and neutrons. So we're going to talk about the strong force a little bit in a very conceptual way. And then we're going to talk about some models that we use to try to represent exactly how the nucleus behaves and how this impacts the binding energy. So once again, the strong force is the force that holds together the nucleus, but actually it is also the force which is holding together the quarks that make up the protons and neutrons. The lower level that we typically teach the composition of the protons and neutrons, the lower level concept that we typically use is we have 3 quarks. We can't separate the 3 quarks. The 3 quarks produce a color, okay, or they produce a combination that results in neutral color. 1 quark is considered to be red, 1 quark is considered to be green, another one's blue. You add them all up, you get white. You get this neutral color charge. Obviously, there's no color involved here, but this is sort of the analogy that they use with these 3 possible charges. So the quarks can't be separated because the strong force will actually become larger and larger as we try to pull them apart. But the quarks themselves, for protons and neutrons, are the up quark and the down quark. The proton has 2 up quarks, which have a partial charge of plus 2/3 e, and a down quark of a charge of negative 1/3 e. And the neutron has 1 up quark plus 2/2, and then 2 down quarks minus 1/3 each. So with our proton, we add up the partial charges. We get a net of 1. 2/3 plus 2/3 minus 1/3 gives us a total of 3/3. If we add the neutrons' partial charges together, 2/3 minus 1/3 minus 1/3 we get to zero. And that's why our proton has an elementary charge and our neutron has no charge. If we go to a higher level of understanding, we see that the quarks inside the protons and the neutrons are not that simple. I think the way it's oftentimes presented is three quarks are bound by these gluons, which are virtual particles that carry the strong force. The reality is the quarks themselves are, in current models, surrounded by these virtual particles constantly popping in and out of existence. If you took the total mass of each of the three quarks and added them together, you would not get the mass of the proton and the neutron. We need this bubbling cauldron of virtual particles popping in and out of existence to produce what we see as the proton and the neutron. And quantum chromodynamics is a field theory that governs this type of interaction. So again, we sort of represent the protons and the neutrons with the simpler model. Or reality, as our experiments become higher and higher energy, and we're able to penetrate into the protons and the neutrons with higher and higher energies, we're able to see greater and greater details of what exactly is going on. In any case, let's go back to the simple model. And again, the protons and the neutrons hold themselves together with the strong force, but the strong force also creates an attraction between protons and neutrons. Again, I'm going to try to keep this model primarily very conceptual. But if we think back to atoms are held together by the electrostatic force. However, when we think about the dipole interaction between molecules, this van der Waals force, that's sort of analogous to what's happening here, that a proton will be attracted to a neutron due to this residual strong force, if you will. And again, this is a great oversimplification of what's really going on here. In some models, we have the protons and the neutrons exchanging these mesons, these virtual mesons known as pi mesons. But again, I think it's best to not go too deep into this and just think about the internucleon force, the force between protons and neutrons as being more of a residual effect of the strong force, much like the dipole-dipole interaction between molecules. The van der Waals force between molecules is a residual effect of the electrostatic force. So once again, how do we build a nucleus? Well, this residual strong force, the strong force itself doesn't really operate on a distance greater than about 1 Fermi. So the protons and neutrons that are right up next to one another are able to interact. But just like in a liquid, particles that are further apart are not going to have as much of an interaction. And this is going to be very, very important to the models that we develop for the nucleus. And one of the reasons why we reach a limit beyond which there's just too much atomic mass. The atomic mass number is too large, the atomic number is too large, and the nucleus becomes unstable. So here is the binding energy for the nucleus. And right off the bat, we see that, obviously a proton is a single particle, so there's no binding energy associated with it. But as we start adding particles, the binding energy per nucleon becomes greater and greater, because in the case of the deuteron, a proton plus a neutron, here we have the interaction of 2 particles. Now, if we go up to helium-3, we have 3 particles interacting with one another. Each particle has a binding potential, which is associated with 2 particles now. And of course, going even further, one of the big increases in the binding energy per nucleon happens at helium-4, but we'll see there's actually some reason why helium-4 is more tightly bound per particle than something like lithium-6 or lithium-7. If we keep following up this curve, we get less and less of an increase in binding energy, as we proceed up to iron 56. Iron and nickel are sort of the point at which we have our maximum binding energy per particle, where on average the particles are most tightly bound. And then we start going downhill again. And really what's happening here is the nucleus is becoming so large, whereas the strong force can act on only a very, very small distance. The electrostatic force has no problem. It can act on as large of a distance as you will. It will drop by 1/r², but we can see the effect that a very large nucleus has this problem with more and more protons being added, creating this electrostatic repulsion. Finally, there's a quantum mechanical effect. It should be that we could add as many neutrons as possible, but due to the Pauli exclusion principle, we will see that neutrons cannot occupy the same quantum state. And therefore, as we add more and more neutrons, we get to a point where the neutrons occupy a higher and higher energy. And by adding them, they'd be just so loosely bound, they would quickly fall off the nucleus. I guess that's not a great way of putting it, but that's one way of putting it. So let's take a look at, once again, where we get this binding energy from, and what effect it has on the nucleus itself. Going back to relativity, we know that the rest mass for a particle is equal to, the rest energy for a particle is equal to the rest mass times the speed of light squared. So when we have two particles bound to one another, the binding energy is negative energy, which means that the two free particles, let's say I have a proton and a neutron free from one another are going to have more energy than a deuteron where a proton is stuck to a neutron, okay? Because a deuteron has less energy, it has less mass by relativity. Because it has less mass, that mass has to be related to the binding energy of the particles. If you want to separate that proton and neutron, again, you've got to add enough energy to effectively add mass so that they can separate and become free particles. So the mass defect is the difference between all the free particles in the nucleus. The protons, Z represents the number of protons, MP is the mass of the protons, and the number of neutrons is A minus Z. So if I multiply that times the mass of the neutrons, that accounts for all the rest mass of the neutrons. And then we subtract off how much the nucleus itself weighs less than the free particles themselves. So again, my mass defect for the deuteron would be the mass of a proton plus the mass of a neutron minus the mass of the deuteron. And we'll find out that there is a difference. Once again, our binding energy is negative energy. It's energy that's been lost because a strong force is holding these nuclei together. There's an interaction with the electrostatic forces too, but effectively, when we bind systems together, the potential energy is negative, and with a potential energy that's negative, that energy has to come from someplace, comes from the mass. It's going to have less mass. So our binding energy is going to be equal to the mass defect, how much lighter this particle is than the sum of all the free particles, times the speed of light squared. Now, if we think about nuclear fusion, we'll get to nuclear fusion later on. And again, we'll use the example of the deuteron because we just have two particles. If I bind a proton to a neutron, okay, and they bind to form our deuteron, energy has to be given up. Otherwise, these particles are just going to go free. So they bind together, they fuse together to produce a heavier nuclei. That energy is typically lost as heat, kinetic energy, whatever mechanism is going to take that away. Again, what's most interesting to look at is the binding energy per nucleon, because this is going to be very, very important for whether nuclear fusion is favored or whether nuclear fission is favored. As we go from the lightest elements up to our peak around iron, okay, we can get energy out of the system because as we keep adding more and more neutrons and protons, okay, the binding energy per nucleon is becoming greater and we're releasing energy into the environment. Once we reach iron, however, we have a problem. I'll go back to that curve. Once we reach iron, if I keep adding protons and neutrons, I'm actually decreasing the energy per nuclei, and that takes energy input into the system to build heavier and heavier elements. On the flip side, if we turn this around, if we go from a very, very heavy nuclei, such as uranium, I split a uranium nucleus into two daughter isotopes, okay? The daughter isotopes are going to be sitting further down this chart right here. They're going to have more binding energy, more negative energy, if you will, more binding energy per nucleon. So by splitting a very heavy nucleus, fission, we get energy out of the system. So again, this binding energy per nucleon, and A represents the atomic mass number, is equal to, again, the mass defect times the speed of light squared times the number of nucleons that we have. So except for, light nuclei, the binding energy for most elements is somewhere around 8 megaelectron volts per nucleon, okay? If you look at this, sort of yellow region, it varies. It almost reaches 9 megaelectron volts per nucleon, but it doesn't really drop far below about 7.5 megaelectron volts per nucleon. So most of the nuclei that we see are somewhere going to be in this range right here, okay? Now, yeah, the lightest elements do have much lower binding energy per nucleon. And, we look at hydrogen. If we fuse hydrogen, which is down here, into helium, there's a tremendous amount of energy that can be released. And that's why fusion, per mass is so much more energetic than fission. Again, curve peaks somewhere around iron. Nuclei with mass number, greater than 60 are not as strongly bound down here. Okay, the amount of binding energy is becoming less and less, and out here you start getting nuclei that will spontaneously fall apart. They'll spontaneously break apart due to fission, or they'll radioactively decay by alpha decay. Again, the curve from right around 40 on slowly decreases binding energy per nucleon, but not a whole lot. That on the other side, actually, once we get to oxygen 16, carbon 12, there's a huge drop off in the binding energy per nucleon. So we're going to look at two very basic models for the nucleus. And when I'm talking about basic, these are very basic with regard to the more complicated models we have according to quantum chromodynamics. One is a semi-empirical model, which means that you kind of come up with terms and you try to fit the terms to your data. And this is sometimes known as a liquid drop model. And the other one is the shell model, where we borrow some of the electronic shell ideas that we had for atoms. So let's start with the semi-empirical model. Basically, if we think of the nucleus as being like a drop of water. We know water droplets will pull themselves into a sphere due to the surface tension. The surface tension is because the molecules at the center of the droplet are being pulled equally from all sides, but the ones on the surface, they are being pulled toward the center, and they want to minimize the surface area. So they're experiencing the greatest inward force. So that is going to result in, sort of the model that we come up with here. First of all, the first term here is the volume term. It's basically the idea that every nucleon, every proton, every neutron is going to contribute to the overall strong interaction that's holding the nucleus together. So that's our volume term. More protons, more neutrons, more strong force, but not necessarily more strong force per nucleon. Okay? The next term is that surface tension term. It's basically, as we grow the volume is going to get bigger than the surface of this droplet, if you will. So the number of nucleons on the surface compared to how many nucleons we have in the center is going to become smaller and smaller. So we subtract off this surface tension term. The next term is due to the electrostatic repulsion. This is the term which is due to the fact that the protons are going to repel one another. So they're going to want to try to tear this whole nucleus apart. And the larger Z becomes, well, the greater this repulsive force is going to become. There's also an asymmetry term. If you get in and this is cheating. I always thought this was cheating. You get a unbalanced number of protons or neutrons. That is going to be reflected in a slight decrease in the energy, because this really relies almost on quantum mechanics. The way we're looking at this is the more neutrons I have, the higher the energy levels that I'm filling in the nucleus. And as I do so, the highest energy neutrons or the highest energy protons are going to have the least amount of binding energy. They're going to have really the greatest chance of being removed from the nucleus if there's some type of interaction that takes place. There's also a parity term. I won't go through that too much, but it also is somewhat of a correction in terms of the neutrons and the protons. So again, semi-empirical model, we think if you increase the number of nucleons, that's going to increase the strong force. We have to take into account that the nucleons on the surface are going to be more tightly bound than the ones in the interior. Volume gets bigger faster than surface area. So this is a correction term. The protons are going to repel one another, so we've got to take that into account. And again, this quasi, almost quantum mechanical term right here also plays a pretty big role too. Now, parity term is basically the ability to pair neutrons and pair protons. Now that is, we'll go back to this. This is somewhat effective in describing what we see here. Again, initially the binding energy per nucleon does go up. There's some variation here until we reach this point, and then we start getting to the point where we have a more significant number of nucleons which are shielded by the surface nucleons, and that surface tension term begins to really take over here, as well as the Coulomb term. So again, that semi-empirical model does give you the overall shape of what we see here, but to come up with it, we're really fitting data to it. The next model is very much related to what we've seen for quantum mechanics already. We know that on the periodic table, as we fill up the electronic levels, this is on the atomic scale, that we get the most tightly bound elements for the noble gases: helium, neon, argon, krypton, xenon, radon are extremely stable. They don't really chemically react with other elements because they have a closed outer shell. Now, if we view the nucleus as being similar, but on a much smaller scale, again, it's not the Coulomb force that's holding these together, rather it's the strong force. So there's more complications going on here than we had with the hydrogen atom and the other atoms. But if we, again, build up this idea that we can fill up levels and that no two particles can have the same energy level, same wave function, okay, then we can come up with a similar model to what we saw before. The shell model is very, very good at helping us understand, some of these different peaks. Like, why does helium-4 suddenly increase in bonding energy per nucleon, where lithium might be down here? Why is carbon-12 more tightly bound than nitrogen-14? Why is oxygen-16 produce a peak right here? Well, again, we can understand these if we understand that we are actually filling up shells, but we have energy levels for the protons, we have energy levels for the neutrons. The Pauli exclusion principle says that no two of the same particle can have the same wave function. So protons will have their own energy shells and neutrons will have their own energy shells. With the electrons, we just had electrons. Now the shell model is based, less on the levels that we got with the hydrogen atom and for the atomic energy levels was based on the Coulomb potential. We solved Schrodinger's equation using this 1/r squared Coulomb potential. Here, the shape of the well is almost more box-like. I guess it would be closer to our harmonic oscillator, which I know is a parabola, but the strong force would be closer in terms of a potential, I guess, to the harmonic oscillator. And again, that's why we label these different shells the way that we do. In any case, I'm not going to go into the details of how we get all these different energy levels and why we have shifts that take place. But basically, think about the shell model as being very similar to what we have with the periodic table of elements. Okay? We have hydrogen, then helium. Helium has 2 electrons, spin up, spin down, and helium is noble gas. We're going to get the same thing with the shell model. Okay? 2 neutrons, 2 protons gives us helium-4, okay? And that will fill up the first nuclear shell, okay? Then again, we go to this model right here. We go to neon, where the next shell will be 2 s electrons and then 6p electrons. So that gets us to neon. So this shell right here, to fill that, I need 8 more electrons. Okay. Here it's a little bit different. Instead, for the nuclear levels, we actually have 6 in that shell. So when we reach a number of 8 protons or 8 neutrons, that particular shell will be closed. And again, you do the same for 20, 28, 50, 82. These are the total numbers. And we call these magic numbers because If our Z equals one of these magic numbers, we've closed the shell for the proton. So it's going to be more tightly bound than, non-magic numbers. If we have that number of neutrons, we tend to have a more stable isotope, for that number too. And we can actually get, in some cases, elements that have a magic proton number and a magic neutron number, which are also very stable. So let's take a look at this. For the proton magic numbers, 2, 6, 8, 20, 28, 50, and 82. No surprise, helium, which produced that big spike, is there. Carbon, oxygen, calcium, nickel, tin, lead. Lead, in fact, is the last element that is still stable. It has the highest atomic number and is still not a radioisotope. Neutrons, we can actually get double magic numbers. Helium is one of those double magic numbers. So we saw a spike there. Carbon 12, another magic number. Oxygen 16, calcium 40. So let's go back to that binding energy. Helium, carbon, oxygen, calcium. And here we go. No surprise. Helium, carbon, oxygen, and calcium is up here someplace. So anywhere where we were doubly magic, 2, 2, 6, 6, 8, 8 in terms of protons and neutrons, we get a higher binding energy. And that nucleus is going to be held together with more energy. Now, here's something that's interesting. Nickel 78 is radioactive. So you're like, well, why are you bringing this up? It's doubly magic, but it can't hold itself together. It's extreme in terms of it's stable enough to have a reasonable half-life. Again, 28 protons for nickel. If we have nickel 28 protons, okay, that's, of course, 50. Yeah, am I getting my number right? Yeah, the number's right here, 50 neutrons. You're getting something which is extremely neutron rich for that double magic number. Okay, so again, just building these different things to see how this works. Helium has a very large binding energy because we fill the first shell. Okay, fusing hydrogen into helium is the most exothermic of all the fusion reactions, because basically you are going from individual particles, free particles, which have the maximum amount of energy, to a closed shell nucleus, which has a very minimal amount of energy. After helium, we reach other elements like beryllium. We want to look at something that's very unstable. Beryllium-8, if we think about this, beryllium-8, why doesn't beryllium-8 exist? It seems like beryllium element 4 protons, 4 neutrons, that shouldn't be all that unstable. But actually it is. And what beryllium-8 tries to do is break itself into 2 helium-4 nuclei, because as you can see here, you have a half-filled shell here, you've got a half-filled shell here. We could simply have these 2 protons and neutrons go off on their own and drop to the ground state and fill that shell. And that's energetically favorable for that to happen. So beryllium-8 is very, very famous for being an extremely unstable isotope that exists for a very brief fraction of a second. Oxygen 16, very stable, not surprisingly, because 8 protons and 8 neutrons fills the first and second shell. Okay, so oxygen 16 has a much higher binding energy than some of the other elements. let's think about this for a second. Yeah, oxygen 16. Calcium 40 is also very stable. It's also a double magic number. And here we can see that with calcium 40, we fill up the next shell. Calcium 48 is a very neutron heavy isotope of calcium that is also fairly stable. So again, how do we explain why some isotopes are more stable than other isotopes? We can use this shell model to help us. But again, the shell model does take into account not only, the wave functions of the protons and the neutrons as they're trapped inside this well. It also takes into account, other factors such as the charge. As you'll see here, notice the protons are slightly, pushed up in terms of their energy level. That's due to the repulsive interaction, the repulsive Coulomb interaction. So your proton energy levels will always be pushed up a little bit higher than the neutron when we're looking at this shell model. So again, without going into too much complexity, we can understand the nucleus, at least the binding energy, in terms of how the neutrons and protons interact, but also the fact that just like the electrons have quantum mechanical levels, quantum mechanics dictates that they have different discrete energy levels. The energy levels of the protons and the neutrons are also discrete. Okay, it'll also be helpful later on when we talk about things like gamma rays. We can have a nucleus where maybe a neutron or a proton ends up initially in one of these higher energy states, and when it drops, a gamma ray is given off by the nucleus.